I want you to try a little thought experiment with me. Just picture your morning routine.
Okay.
It's early. You're still kind of groggy. You go into the bathroom, you brush your teeth, maybe hop in the shower. You turn a handle, water just appears. And then when you're done, it just vanishes.
It just goes away like magic.
Exactly. You flush the toilet, and with this swirl and a gurgle, it's gone.
That's all.
It's gone. We treat it like magic. But, looking at the sources we have today, it is very clearly not magic. It's a machine.
Oh, it is absolutely a machine. A really elegant one, too. It's gravity-fed. It's balanced by atmospheric pressure, and it runs 24/7 inside your walls with not a single motor.
And that is exactly what we are digging into today. We're looking at the unsung hero that makes all of modern hygiene possible, the DWV system.
Which stands for drain, waste, and vent.
We're basing this whole deep dive on a technical breakdown we found from Plumb Talk, and it's this really comprehensive guide for residential installers. And I have to say, reading it, I realized I've been taking my walls completely for granted.
Well, most people do. I mean, until it stops working.
Right.
And then it becomes the only thing you can think about.
So our mission today is to, metaphorically, strip the drywall off the house and just look at this highway system inside. We're going to try to understand the physics, the chemistry, and the surprisingly precise math that keeps sewer gas out of your bedroom.
And that's a very real threat. I think people forget that the only thing separating you from the city sewer is a little bit of water and some really clever engineering.
So let's start with the name, DWV. Drain, waste, vent. I think most people, myself included, kind of assume drain and waste are, synonyms.
Yeah, just dirty water.
Right. But the source makes a really sharp distinction, doesn't it?
Oh, they're very distinct. In the trade, mixing them up is it's a rookie mistake. Drain refers to what we call gray water.
This is the relatively clean stuff.
Relatively, yeah. It's water from your sink, your shower, your washing machine. I mean, it has soap in it, maybe some hair, but physically, it's just a liquid. It flows like water.
Okay, so waste is the heavy hitter.
Waste lines, or what the old-timers in the trade call soil lines, they handle the solids. This is pretty much all coming from water closets.
Water closets. I love how formal the plumbing code is. We mean toilets.
We mean toilets. But, the distinction matters because the physics of moving a solid through a pipe with only gravity is, well, it's totally different than just moving liquid.
You need different pipes.
Different pipe sizes, and you have to respect the flow completely differently.
And we were definitely going to get into that flow math because it's honestly counterintuitive. But, okay, so we have D for drain, W for waste. That leaves V vent.
The secret sauce.
This was the biggest wait what moment for me in the reading. I get that pipes go down, gravity pulls water down, but why on earth do we need pipes that go up?
Because your pipes need to breathe.
Breathe, like lungs.
Kinda. Think about it this way. You've taken a straw, right? You put it in a drink, you put your finger over the top hole, and then you lift it out.
Sure, and the liquid stays in the straw.
Why?
Because...
Basically, yeah. It's atmospheric pressure. The air outside is pushing up. And because no air can get in from the top to replace the liquid, gravity loses.
Okay, yeah, I'm with you.
Now just imagine your main sewer pipe is that straw. You flush a toilet, that's a slug of water and waste, maybe 1.6 gallons, rushing down the pipe. It acts like a piston. As it drops, it creates this massive vacuum behind it.
So it's trying to pull air in from somewhere to fill the space it just left.
Exactly. Nature abhors a vacuum. So if you don't have a vent pipe going up to the roof to let fresh air in, that vacuum is going to pull air from the path of least resistance.
And that path is...
your P-traps.
Right.
That little U-shaped bit of pipe under your sink, the vacuum will literally slurp the water right out of it.
So a flush downstairs could actually suck the water out of a sink upstairs.
Which happens all the time in houses that are vented badly. You hear that gurgle in the sink when you flush a toilet.
Oh, I always thought that was the sound of water moving.
Nope. That gurgle is the sound of air being violently pulled through the water in your trap. It is the sound of the system failing. And once that water's gone...
the seal is broken.
And the smell comes in, the methane, the bacteria. The source is very clear on this. The trap seal is the most critical safety feature in the whole system. Without a vent to protect it, the trap is useless.
That's wild, that we have this whole network of pipes going up to the roof just to protect a little cup of water under the sink.
It's a balancing act. You're balancing the downward force of waste with the downward flow of air. If they don't match, the whole system chokes.
Let's talk about the hardware, the little pipes themselves. The source focuses a lot on Schedule 40 PVC. That's the white plastic pipe you see everywhere.
Right. If your house was built after, say, the early 90s, this is almost certainly what you've got in your walls.
And before that, it was all cast iron.
Cast iron, yeah. Heavy black cast iron.
So why the switch? Was it just that smooth bore? Sounds like a weapon spec.
It kind of is. It refers to the interior surface of the pipe. Cast iron, over time, it rusts, it gets pitted, that texture grabs onto, well, things.
Solids. Grease.
Right. It creates drag. PVC it's chemically inert. It's like glass on the inside. So friction is almost zero, which just helps everything slide away much faster.
Though I will say, the source did mention one downside to EVC. The noise.
Oh, the whoosh. Yes. Cast iron is so dense it muffles the sound. PVC is light, so if a builder doesn't insulate those walls properly, you can hear exactly when someone on the second floor flushes the toilet.
A small price to pay, I guess. So we have the material. Now I want to try to visualize the layout. The source describes it almost like a tree.
That is the best way to think about it. You have a main trunk and then all the branches.
Okay, let's start with the trunk.
The trunk is the main soil stack. In a 2-story house, this is the spine. It's usually a 4-inch diameter pipe, sometimes 3-inch in newer codes, that runs vertically from the basement all the way up through the roof.
And it's hidden in what they call a wet wall.
Correct. When framers build the house, they'll often use 2x6 studs instead of 2x4s for certain walls, just to make enough space for this massive pipe.
Which is why bathrooms are often stacked on top of each other.
Exactly. Or back to back with the kitchen. It's all about efficiency and gravity. You want the shortest, straightest path to that main stack.
So, branching off this main stack, you have the fixture arms. This is where the sizing gets really specific. Toilets are the heavy hitters.
Oh, yeah. You
Okay.
cannot put a toilet on a 2-inch pipe. It just won't work. A toilet needs a minimum of 3 inches, preferably 4. It's carrying solids. It's a high volume, instant discharge.
And then you step down from there.
Right. Showers and tubs, they usually get 2-inch drains. Sinks, both in the kitchen and the bathroom, they're the little twigs on the tree. They usually have a 1.5-inch trap that then ties into a larger branch.
It's the whole hierarchy. Small streams feeding into rivers, feeding into the ocean.
And managing that whole system is the job of the rough-in.
I love that term, rough-in. It sounds so aggressive.
It kind of is. It happens when the house is just a skeleton. No drywall, no insulation. The plumber has to walk in and solve this 3-dimensional puzzle.
And they can't just drill holes wherever they want.
Oh, absolutely not. If you drill a 4-inch hole right through the middle of a load-bearing floor joist, you might have just compromised the entire structure of the house. So it's a negotiation.
But here's the kicker. They have to do all this dodging and weaving, while maintaining a perfect slope.
The pitch, yes.
Yes.
This is the part you cannot get wrong.
Let's get into this because this was the physics lesson I didn't expect.
Yeah.
I always just assumed that with drainage, steeper is better.
You'd think so.
Right. If I want water to go away, why not just point the pipe at like a 45-degree angle? Whoosh.
No.
Gone.
But see, we're not just moving water, we're moving solids, suspended in water.
Okay.
If the slope is too steep, the water moves incredibly fast. It spreads out into this thin little ribbon at the bottom of the pipe, and it moves faster than the solids.
It runs away from the waste.
It leaves the waste behind. The liquid rushes off to the sewer, and the solids get stranded. Then they dry out, they stick to the pipe, and boom, you've made a clog.
That is fascinating. So the water has to move slow enough to carry everything with it.
We call it scouring velocity. You want the water deep enough and turbulent enough to basically float the solids down the river. You need the river to carry the log, not rush out from under it.
So what's the magic number? The Goldilocks zone.
For pipes 3 inches and larger, so your toilet line, the standard is 1/8 of an inch of drop per foot of run.
1/8 of an inch. That's barely anything.
It is incredibly subtle. Over a 10-foot run, that pipe only drops a little over an inch. It keeps the water moving at about 2 feet per second, slow and steady.
And for the smaller pipes, sinks and showers.
For those 2-inch pipes and smaller, you can go a bit steeper. 1/4 inch per foot is the minimum. There are no solids, so you want that gray water to clear out faster to prevent soap scum from building up.
So, the precision required for what looks like just rough work is actually incredibly high.
It is. It's geometry, but in the real world, with real consequences if you get it wrong.
Speaking of geometry, the source talks about turning corners. You can't just use a sharp 90-degree angle.
Not for drainage, no. In the supply lines, the ones under pressure bringing clean water in, you can use sharp elbows. But for the drain, think of it like a bobsled run.
Okay.
If you hit a sharp wall, you crash. Solids. They do the same thing. They slam into the wall, they lose momentum, they get deposited right there.
So you use what they call long sweep 90s?
Long sweep 90s or two 45-degree fittings to make a nice gentle turn. You just want to smooth the path.
Okay, let's loop back to the vents for a second. We know we need them. But does every single sink need its own pipe going all the way to the roof? That would look insane.
It would look like a pipe organ on your roof, yeah. No, the design gets clever here. Use things like common venting.
Explain that.
So if you have, say, two sinks back to back in a wall, they can share a vent. The air comes down one pipe and just splits off to serve both of them.
And what about wet venting? That term sounded like a contradiction.
It is a bit complex, and honestly, it's where a lot of apprentices get confused. A wet vent is a pipe that is acting as a drain for one fixture, like a sink, and a vent for another fixture, like a toilet, at the same time.
So water and air are sharing a lane.
They are. But it only works if you oversize the pipe. You have to make sure the pipe is big enough so that even when the sink is draining, the pipe is only about half full of water.
Ah, so the bottom half is the river and the top half is the air tunnel.
Precisely. The top half is still breathing for that toilet.
But eventually, all these vents, wet, dry, common, they all meet up somewhere.
Usually in the attic, yes. They combine into one, maybe two main stacks that punch through the roof.
And the source says it has to stick up 6 to 12 inches above the roof.
Right. High enough that snow can't cover it in the winter. Because if that vent gets plugged,
The vacuum comes back.
the engine stalls. Yep. The whole gravity machine just stops working right.
Okay, so we've designed the machine. Now we have to build it. And this takes us to the chemistry of it all. Because you're not screwing these pipes together.
No. No threads, no gaskets. We're doing what's called solvent welding.
Which I think most of us just call gluing.
Yeah, we call it glue, but that's really a misnomer. Glue is an adhesive. It sticks two surfaces together, this chemical fusion. The primer and the cement, they literally melt the plastic
Melted.
on a molecular level. It breaks down the surface of the PVC. When you push the pipe into the fitting, those two liquefied layers mix together. As the solvents evaporate, it hardens back into a single solid piece of plastic.
It actually becomes one continuous unit.
It does. If you do it right and you cut a cross-section, you often can't even see the seam. They're fused.
So walk us through the process. Because the source makes it sound like a ritual.
It is a ritual you cannot rush. First, you cut the pipe. Then, and this is the step everyone skips, you have to deburr and bevel the edge.
Bevel, meaning you shave it to an angle.
Yeah, a slight angle. Because if you have a sharp, square edge on your pipe, when you push it into the fitting, it acts like a squeegee. It scrapes all the cement off the sides.
Oh, wow.
A beveled edge rides over the cement and keeps a layer between the parts.
Okay, so you're prepped. Now comes the purple stuff.
The purple primer, its job is to clean, but more importantly, to soften the PVC. It starts the chemical reaction, you apply it, and then immediately, while it's still wet, you apply the cement.
And you got to be fast.
Very fast. You swab the fitting, you swab the pipe, you push them together, and you give it a quarter turn.
Why the turn?
To spread the cement evenly. And then, this is the part amateurs always miss. You hold it. You have to hold it.
For how long?
About 30 seconds.
Why? It's going to fall apart.
It wants to push back out. The fitting is tapered, it's a tight fit, and the chemical reaction creates heat. We call it push out. The pipe literally tries to reject the fitting.
So if you don't hold it.
You'll come back 5 minutes later and find the pipe has pushed itself out by ½ an inch, and now you have a permanent leak.
That adds a layer of stress.
It keeps you humble.
So you've done all this. The whole system is glued up. The house is still a skeleton. There's one last step before the drywall goes on. The final exam.
The pressure test. You have to prove it holds.
How do you test a system that's designed to be open to the air?
You plug the holes, you put these inflatable balls in the pipes, and then you have two options. The most impressive one is the water column test.
Describe that for us.
You take a garden hose up to the roof, you stick it in the vent stack, and you fill the entire system with water. The entire house, all the pipes, until it spills out the top of the roof.
You fill the whole house with water.
Every inch. The pressure at the bottom is immense. If you have a single bad joint, it will spray.
Talk about high stakes.
Better to find it now than after the new hardwood floors are in.
So when you see that inspector walk in, look at the gauge or see no drips and sign off. That must be a huge relief.
Yeah. It is. It's the green light. It means the circulatory system is alive and well.
It really is incredible. It's this complex, silent, passive engine running on gravity.
And if it's installed right, that PVC will probably outlast the mortgage. Easily 50 years.
Assuming, as source Riley notes, that no one flushes inappropriate stuff.
Right. The engineer can't control the toddler with a toy truck.
Or the so-called flushable wipes.
Oh, don't get me started on those.
We'll save that for another time. But really, it changes how you look at a simple flush. It's not just a handle. It's a trigger for this incredibly precise chain reaction.
A reaction that connects your private home to this huge public infrastructure.
We hope this deep dive helps you walk away with a new appreciation for what's going on inside your walls. The next time you hear a gurgle in the sink, you won't just be annoyed. You'll be diagnostic. You'll know, aha, my house is gasping for air.
Exactly.
And that leads me to one last thought I want to leave everyone with. We talked about that little curve of pipe under the sink.
The barrier.
I want you to think about this tonight. That little cup of water, held there by nothing more than gravity and proper venting. That is the only thing standing between the sanitary safety of your home and the toxic, explosive, bacteria-ridden gases of the entire city sewer system.
It's not a steel door. It's not a filter. It's just a cup of water.
That is actually kind of terrifying.
It is. It's fragile. So the question is your vent clear enough to hold it there? Or is the next flush going to be the one that breaks the seal?
On that slightly ominous note, thank you for joining us on this deep dive into the hidden circulatory system of your home.
Stay curious.
We'll see you next time.